Very good morning to all of you. I hope I'm audible and the screen is visible. Welcome back to the last leg of the course and your semester as well. I have been receiving emails from various project groups. I think I have tried to reply to all of them. In case I have missed replying to a particular email, especially for the project, please let me know. And scribes for today's class, ID number 118. Are you there? 118, 120, 121.
Yes, sir.
Okay, 122, 123.
Yes, sir.
Okay, and 124. Okay, only two are present. I think I'll wait for a couple of more minutes and then we'll begin.
Sir,
Yes.
I have a doubt in the previous tutorial.
Okay, go ahead.
It was a question about vector spaces.
Mm-hmm.
It was asking how many vector spaces are there whose elements all come from R square, such that both 5, 11 and 15, 33 belong to the vector space.
Just a minute. I'll write down the numbers. Once again, which are the elements?
5, 11
5, 11.
and 15, 33.
Okay. Yes, go ahead.
So it was asking how many vector spaces are there whose elements uh, means which
Which
these elements.
contain these two elements at least.
Yes, sir.
Yeah, so what is your answer?
So I'm not able to like uh, uh, understand the question, like how to begin.
Right. So let's look at the definition of the vector space. So I'm not going to go through all the details. In case you have a doubt, I mean, this is for the entire class. We have gone through this in details before Diwali. I hope this is understandable. Now try to think that with these two elements alone, will I be able to satisfy all these axioms where I'm given that the set is R2, right? So for example, if I just consider this set 5, 11 and 15, 33, right? Will it satisfy all these axioms? For example, is the additive identity in this set? So to be honest, question is, it assumes that you already know what is the binary operations over here. But if I assume that you all are familiar with the usual addition in R2 and multiplication by a scalar with an element of R2, then do you think this set will form a vector space? This set that contains only these two elements. Kandar?
Uh, yeah.
only this set, huh? I mean, the set that contains these two elements. Does it have the additive identity?
Yes, if we multiply
Additive
scalars
identity,
to,
not asking
yeah,
you. Yeah, go ahead.
no additive identity.
Right. So what would be the additive identity? Has to be this,
Zero.
right? 0, 0.
Yes.
So you need to include at least this. Then what else? Is this set closed with respect to vector addition and scalar multiplication? These two axioms. So for example, if I multiply this particular element by, I don't know, square root 2, right? The resultant would be root 2 5 and root 2 into 11, right? This element, of course, is not in this set,
Yes, sir.
right? So you'll have to include all multiples of this element and this element for the set to become a vector space, right?
Yes, sir.
All right. So what else can happen? So if I were to represent this element, this is your R2, right? X and Y. This is your 5 comma 11. If you notice, 15 comma 33 is nothing but
On the same line.
on the same line. So you'll at least have to include this entire straight line, right?
Yes, sir.
Yes, at least this. So would this entire line form a vector space? You can see, does it form an abelian group with respect to the plus operation?
Yes.
If I take, right,
Yes,
if
sir.
I take any two elements on the line and if I add them, it will still have an element on the line, right? The addition operation, of course, is commutative. For additive inverse, I mean, if this is the element, then I have to basically look at the opposite element. So additive inverse also exists, additive identity exists. The plus operation as defined is associative and commutative. Right, so therefore it forms an abelian group. This of course is closed with respect to scalar multiplication. This has nothing to do with this set. So one of course exists in the set of real numbers. Distributivity you can check, it will satisfy, and similarly compatibility of field and scalar multiplication is also satisfied. So this will form one vector space. But are there any other vector spaces that contain these 2 points also in R2? Right. So one thing is for sure, any other vector space will have to contain this blue line for it to form a vector space. It cannot be smaller than this, right?
Yes, sir.
So what is the other vector space that is possible?
The XY plane.
Sorry?
The XY plane.
The XY plane or R2. Right? That I'm not sure that have we looked at this, but R2 also is a vector space, right? Can check again these properties, it will satisfy. So the short answer to your question is 2.
Okay. Yes, sir. Got it.
All right.
Sir,
And
can't we have Q2 as vector space?
Q2, but the set given to you is R2. So by default, if R2 is given, then the field, right, should be assumed to be R.
Sir, but the elements are coming from R2, but it is not said that the field is R2.
No, so that's what I'm saying. So if it is not specified in the question, what is the field? In that case, you should assume that if the set is R2, then the field is R.
Okay, okay, sir. I thought that we have to arbitrate. We can choose field by
Right.
ourselves.
Yes. So the problem in the second module or second part of the course is that me and Rahul are sort of getting a little asynchronized. So he has already taught you taught that particular section, some concept that we are going to discuss in class today. And since I have not taught you this particular concept, this is the only way in which he could put this question, okay, without introducing a new terminology. So be assured that such a question will not come up ever. Right? There is a better way to put the same question, better formulation of the same question. The issue was till the last tutorial, I had not covered that particular concept. Okay, so hopefully in about 10-15 minutes, you will understand the question, the same question in a better way. Okay, yeah. Any other doubts? Okay, then guess let's get started. Any problems with the vector space definition? Okay, any issues with definition of what is a field? And a field is a set with two binary operations, class F, and multiplication between elements of this set, which satisfies these three properties. Okay, so this is something we did in the last class. Let's look at examples of fields also we saw in the last class. As far as notation is concerned, an arbitrary field, right? So if I don't specify a field and if I'm working with abstract vector spaces, in that case, the field will be denoted by this particular F. Okay, and if I give you a set with these two binary operations and this particular field, if it satisfies all vector space axioms, we say that this triplet forms a vector space over F. Okay, and once you have a vector space, any element of the set V will be referred to as a vector, and any element of the field will be referred to as a scalar. Right, I think this is what we did till the last class. Any doubts at all? Okay, take that as a no. And then let's look at examples of vector spaces. I don't think we looked at examples of vector spaces, right? So the set R is the set of all real numbers with your usual real number addition and usual multiplication of two real numbers. It also forms a vector space. Right? I'm not going to prove all of this in details. Right? I think this should be fairly straightforward. Right? And in general, by the way, if I give you a field, okay, right, then this field also forms a vector space over the field F. Right? I hope that is clear. We try to run through the axioms of the vector space and see if this makes sense. It's a field, so of course F with plus F is an abelian group, and that's a requirement for F to be a field, plus there is scalar multiplication identity, because F minus the additive identity is also an abelian group with respect to multiplication. So of course there has to be an identity. What else? Distributivity comes from the field axiom itself, right? Just back to that, right? This is sort of capturing distributivity in the vector space also. Okay. What else is required? Check this, right? This is and this, because the dot and the multiplication operations are the same, right? So as far as this example is concerned, compatibility is basically saying this: A cross P cross U is equal to A cross P cross U, right? And that comes by associativity of your field multiplication, right? Is that clear? Or do you want me to discuss this in more details? If you want, we can sort of pause for a couple of minutes.
So can you show the compatibility axiom?
Sure.
Okay, sir.
So remember, this is your field multiplication, this is your scalar multiplication, which in this particular example is the same. Okay, anybody else? Then let's move ahead. General, so Rn over R or Fn over the field F, okay, where the field addition, sorry, the vector space addition is defined in this way. And the scalar multiplication is defined in, this is a definition, okay, in this way. The addition, scalar multiplication. If I define these two operations in this particular way, I hope you can see that this in general will also be a vector space. No matter what your field is, the set of n tuples of your field elements will also form a vector space. Again, if you want me to look at or prove all the vector space axioms, we can do that. I guess it should be straightforward. Does anybody want to sort of go through the details of this example? Details. That all right?
Yes.
Okay. Uh, so of course, this is just another example of the same general example. C is the set of complex numbers is also a field. So Cn over C is also going to be a vector space. Right? If the previous example is clear, then these two are just specific examples of that case. You can also have a vector space where the set V is Cn and the field is R. Okay, so although most popular and common examples of vector space that you will encounter will always have a very close association with the set V and the field F, can be slightly different in some cases, as this example shows. Okay, again, we mentally try to go through the vector space axioms for this example. So Cn with plus, okay, again, I'm not yet defined that. Let me just write it maybe. X1 plus I by 1 to x n plus I by n plus p1 plus I by q 1 en plus I q n. The addition will always be defined. Unless specified, this will always be this. Okay, so add corresponding components. Okay, and all of these additions are just real number additions. Okay, so I'm using the field addition in order to define this operation. Any doubts here? Any particular axiom that you feel is difficult to show in this case? Then we can go through that particular axiom. Is there any particular axiom you want me to discuss? You want me to sort of hold for a couple of minutes for you to work out the details? Okay, then let's move ahead. RZ, so this again is not a very standard notation. It's something that I just came up just because I didn't have a better notation. Right? So you won't find this notation most likely in any books. Okay? The RZ is nothing but a set of all doubly infinite sequences. So what I mean by this is, if X is an element of this set, right? X is something like this. X minus 2, X minus 1, 0, X1, X2, and this continues. Okay, so the index basically goes right up to plus infinity in this direction and minus infinity in this direction. Okay, so this would be just one element. Okay, please be careful. each element of this set is a doubly infinite sequence. Right? And why this example is pertinent is because you probably have seen this set in your other course, right? Have you come across this example? And of course, not in the context of vector spaces.
Yes, sir.
Right? This is nothing but a discrete time real valued signal. Okay, and here again, I'm not writing this, but the vector space addition would be your element wise addition, and scalar multiplication is again element wise multiplication with real numbers or with the scalar. Okay, any doubts in this? Again, remember, since this is a vector space, each such sequence will now be called a vector. Okay, till this example, I think it's still intuitive to see that every element of this four sets can be called a vector. But now, even a sequence, right, is a vector. Shall we move on to the next example? PR. Okay.
Sir, you said that sequence is a vector. So that
Yes.
whole sequence was a vector, like that
Yes.
X element.
Yes.
Okay.
So this entire sequence is one vector. A different sequence is another vector. Okay, compare this to your R2 case. R2, if X is an element in R2, it basically is a tuple X1, X2. Right? This we can sort of interpret it very easily as the vector as we have been familiar with, right? This is a vector if there is another element in R2, it has components y1, y2. Okay, this is another vector. All right.
Yes. Yes.
So basically, you should see this example as just an extension of Rn. I mean, why should we stop only at n components or n tuples? Right? Let that n tend to infinity, you get sequences. That's basically how it is. Okay, so next example, again, as far as vectors are concerned, this is very unintuitive to all of us. The set of all polynomials of one variable with real coefficients. That again forms a vector space over the field R. Okay, here how will we define addition? Let P be a polynomial of, so once we say it's a polynomial, what does that mean? Means it has to have some degree, right? Let's say this is degree n. And there is another polynomial. And of course, it's not necessary for the other polynomial to also have the same degree. It is qmxn. Then what is p plus q? How should we define this vector addition? Okay, we define vector addition as giving a polynomial again, right? Remember, we want the set to be closed with respect to vector addition. So if I have the set of polynomials, if I take two arbitrary polynomials, I should be able to define this addition so that the resultant element is also in the same set, which in this case happens to be the set of polynomials. So how do I define this? Define it in this way. P0 plus Q0 plus P1 plus Q1x, so on and so forth. Let's say plus P min, and to assume that m is greater than n, equal to n, so that is Pn plus Qn x to the power n, so on and so forth, Qm x to the power n. Here, I'm just doing a coefficient-wise addition. Any doubts here? How about scalar multiplication? What should A dot P be?
Some another.
Another polynomial, right? So, but how do I define? Just saying that A dot P belongs to PR is not enough. I need to define this operation. So, what is A dot P? I'll have to define it.
A is
And
multiplied to every coefficient.
exactly. P0 plus A P1 x, so on and so forth, A Pn xn. Right. So these two. So I hope this notation is clear to everyone. This notation means whatever is on the left is being defined according to whatever is on the right hand side. Right? Are all of you familiar with this notation?
Yes.
Okay, great. Right. So with these two vector space or with these two binary operations defined in this way, I think it should be fairly easy to show that the set of all polynomials satisfy all the vector space axioms. Okay, once you do that, again, every polynomial can be thought of as a vector. All right. Let's look at a couple of examples that you have already hopefully studied. L2R over the field of complex numbers. Okay, what is L2R? Is the set of complex valued absolute square integrable functions. Have you come across this?
No, sir.
No, oh, that's strange. Okay. L2R is the set of functions whose domain is set of real numbers, whose codomain is set of complex numbers, such that this integral is finite. Now, does it ring a bell?
Yes, sir, in Fourier
Yes.
transform.
Exactly. Yes. Finite energy signals, right? That is how you call it in signals and systems. Right. So this is also known as finite energy complex value signals. We are not going to prove that this is a vector space, you will sort of need a little bit more in order to show that this is a vector space. That extra concept is something I'm sure you've studied in your signals and systems course. You have come across Cauchy-Schwarz inequality?
No, sir. No, sir.
No, okay, fine. Then, yeah, that is something that will be required for us to show that this is a vector space, right? In specifically speaking, if how do I define vector space addition here? So let's say let F and G be two finite energy signals or square integrable complex valued signals. And how will I define F plus G? Right? F plus G must also be a complex valued signal defined on R, right? So how do I define this? So this has to be a function. How do I define a function? I define it by specifying what is the value that this function takes for every real number t. That I'm going to define it in this way. For all real numbers. Right now, the only thing is f plus g, the way we have defined it, is surely a function from R to C. But what is the guarantee that this signal f plus g will also have a finite energy? Right? So I also need to show this. Is also infinite, given that this is finite and this is finite. Okay, so this we will assume for now. Later on, once you come across the Cauchy-Schwarz inequality, you will be able to show this yourself. Okay, so but for the time being, just assume that the way we have defined this vector space addition, and of course the scalar multiplication is defined this way. A dot f is a function which at the real number value t is defined as this. F at t is the value of the function at time t multiplied by the complex number a. Okay, and f at t is also a complex number. Multiplication of two complex number will be a complex number. Okay, so with scalar multiplication and vector addition defined in this way, L2R, okay, also is a vector space. Okay, yet another example of a vector space that you have come across hopefully in your signals and systems course will be the small L2 over C. The small L2 is nothing but the set of complex valued absolute square summable doubly infinite sequences. Right? Have you come across this example? Let me write it in a way that hopefully you can recognize. Now, does it ring a bell?
Sir, in the LTI systems, it is a condition for it to be stable.
No. So As of now, we have not even talked about linear systems at all. In the language of signals and systems, we are only looking at signals for now. Right? As of now, we have not talked about transforming signals at all, right? Or transforming vectors
Energy
at
of
all.
discrete time signal.
Yes. So these are nothing but complex valued finite energy discrete signals.
Yes, sir. Yes, sir. Finite energy of discrete signals.
Exactly. Complex valued finite energy discrete signal. That in general is denoted by small l2. Okay. Which book are you referring to, by the way, for signals and systems? Are you referring to a book at all? Is there a silence? I mean, wasn't a very difficult question. What is the book you're referring to for signals and systems?
That is Alan V. opinion.
Oppenheim and Schaffer, or Oppenheim and Wilsky. Okay, so don't know if you go through the book, most likely you will see these notations. Capital N2 is for continuous valued signals, which are finite energy. Small l2 is for complex valued absolute square summable sequences. Okay. Anyways, once again here I am not proving that this is a vector space, but since you are working with these examples in different courses, I thought it's important for you to realize that this is a vector space. Okay, and remember, I mean, I'm sure you have seen things like adding two signals, right? Multiplying a signal with a scalar. Is that true?
Yes, sir.
So you're basically using vector space operations there. Okay, so what I want to convey is, unless you have a vector space, you do not have signals and systems. Okay, for example, convolution, right? I'm sure you by now have studied convolution. You cannot do convolution unless you have a underlying vector space. All right. So, and we'll look at convolution later on, hopefully, if time permits. But for now, I just wanted to show you that whatever you are doing in signals and systems, you are sort of building on top of a vector space. Okay. So that is all I want to convey. Again, a different example of vector space is the set of all m cross n matrices with real valued entries. Okay, once again, capital M cross N, R denotes the set of all m by n matrices with real number entries. Okay, that also forms a vector space, and I don't think it is very difficult to see what should be the vector space operations here. So, can you guess, or something more than a guess? What should be the vector space addition operation here?
Matrix addition.
Matrix addition, what does that mean?
Element to element addition.
Exactly. Add corresponding entries of the matrices. That should be your vector space addition. Scalar multiplication.
Multiplying
All.
all elements with same number.
Exactly. So that is your scalar multiplication. Again, I think I can leave this as an exercise. for you guys to show that this will form a vector space over R. Okay, so I'm just trying to give you as different examples as possible, some of which you may encounter in other courses as well. Right, so is it clear what is a vector space? I hope I've given enough examples of vector spaces as well. So, yeah. Next thing is now, unless you guys have any doubt, to look at special subsets of vector spaces. Okay. So, let's look at the definition of a subspace. Okay. So, if I give you that V is a vector space over some field F, a subset of this vector space, let's say W, okay, will be called a subspace of this vector space V if that subset with the same binary operations. Okay, this is important. With the same binary operations. I think this was a bad idea. This and this have to be the same as this and this. Okay, if this subset with the same two binary operations is also a vector space over the same field F. Okay, if that is the case, then we say that the set W is a subspace of my vector space V. You have seen a similar definition in our course earlier. Can you recall the concept?
Subgroups.
Subgroup.
Exactly. So this is just analogous to subgroup. Okay, in subgroup and groups, there was only one binary operation. In vector spaces, there are two binary operations. That's the only difference. Okay. So just a small notation for subspaces. I will use capital letters to denote subspaces, and the same alphabet or the same letter, if I write it as a small letter, then it will denote a vector or an element of that set. Okay, so don't get confused. I will just use U or small u without stating which is a subspace, which is a vector. Right? All subspaces, at least in my course, I will always denote it by a capital letter. Okay, and vectors or elements of the set, I will always denote it with small letters as far as possible. Okay, let's look at examples of subspaces. Okay, so remember again the definition says W has to be a subset of V. It doesn't say that W has to be a proper subset of V. Okay, so a set is a subset of itself, and that is why the set V itself will also be a subspace. And similarly, a set that contains only the additive identity of the vector space, that singleton set will always be a subspace again. Okay, so these are two examples of subspaces, no matter what your vector space is. Right? Maybe again do a mental check. This shouldn't be difficult, right? Because we have already, it is given that V is a vector space over F. Okay, so of course it satisfies this definition of a subspace. How about the second example, theta? Is it an abelian group with respect to addition? Of course it is, because the only element it has is the additive identity. Okay, how about the other vector space axioms? 1 into theta is of course theta, right? So theta of course is in theta. Okay, so again, maybe I'll give you 2 minutes to go through the vector space axioms to show that this singleton set will always be a subspace. In case you have any doubts, please let me know. And let's maybe look at more examples of subspaces. And by the way, these two subspaces will be called trivial subspaces. This is again analogous to trivial subgroups. Okay, the group itself and the singleton set containing the identity element, they always are subgroups for any given group, and these two subgroups are called trivial subgroups. Similarly here, the vector space set V and the singleton set that contains the additive identity, these are always subspaces and they will be called trivial subspaces. Okay, so let's look at more specific examples of subspaces. Okay, so let's take R2 because that's sort of the example of vector space that we have been using right from our school days, the XY plane. Let us take a subset of this R2. So this is again directly connected to that particular tutorial question that we started discussing at the beginning of the class. This set W, can you identify what is this set? I'm sure you should be able to do it. What is this W?
Line.
A line. Do you think a line in R2 will be a subspace?
Yes.
Yes.
Yes. Fine. So let's take this line. Will this line be a subspace?
To pass through origin.
Yes,
Should
sir.
pass.
See.
Oh, so this should be a subspace. So let's look at closure with respect to scalar multiplication, let's say. If I take this element, right, let's call it U. 0 into U is what? This has to be theta, right? Okay, this theta, which is the additive identity here, in this case, it is just 0, 0. So it's the origin. Does the origin belong to W? No. So U is not a subspace. Is that clear?
So then any line which may be passing through origin would be a subspace?
Exactly. So my question is, what should be the value of C for W to be a subspace?
So C equals 0.
C has to be 0, of course. Good. Okay, so W is a subspace if and only if C is 0. Okay, that clear to everyone? How will you prove this, by the way? So remember, you will have to show each and every vector space axiom is true. Okay. Any doubts in this particular example? Note that A and B can be arbitrary, but they are fixed. So if W doesn't necessarily have to be a line. Okay, for example, if A and B are both of them put to 0, then what would W be?
So it will be whole R square plane.
Exactly, it will be the entire plane. Okay, but as far as C is 0, W will always be a subspace. Okay, so bringing this back to that tutorial question Rahul wanted to ask is, what are the subspaces that contain those two elements? Right, I think the elements given were 511 and 1533. Right, so the question he specifically wanted to ask is, give all the subspaces that contain these two elements. But unfortunately, since we did not define subspaces, so he couldn't put it that way. But if you look at the definition of subspace, subspace is nothing but a subset of a vector space, which itself should be a vector space. So that is why he put it that way. Is that clear? Andar?
Yes, sir.
Okay. Let's look at other examples of subspaces. So let's take the set of all polynomials that we introduced in the last couple of slides. Let us take a subset of it, calling it W, where W is nothing but PNR, where PNR denotes the set of all polynomials of one variable with real coefficients, but with degree at most n. Okay. So in the vector space V, we are not limiting what the degree of the polynomial is. It could be any finite number, 10,000, 10 million, billion, whatever, it doesn't really matter. Let us take, if I take n to be 10, then I'm considering the subset that contains all polynomials with degree at most 10. Okay, it could be degree 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Will that subset W form a subspace? Right, so in principle, we are supposed to check all these properties. Okay, now think about this. This is again analogous to the subgroup case, right? How did we define subgroups? A subgroup is nothing but a subset of the group, which is itself a group, right? That is the definition, isn't it?
Yes.
But then we also saw that we really need not look at all the group axioms, because if on the larger set all group axioms are satisfied, then on a smaller set some of the group axioms are automatically satisfied, right? For example, associativity. So we need not really look at associativity if we want to show that a subset of the group is a subgroup. Same manner here, the definition of subspace is that that subset should also be a vector space. But remember, the larger set is already given to you to be a vector space. So which of these axioms do I need not even care about if I want to see whether a subset is a subspace?
So the last step,
Compatibility.
Compatibility is of course guaranteed, right? How about distributivity?
it is also guaranteed.
Yes.
It is also guaranteed. So let's not check that. Scalar multiplication identity?
It is
It
also.
is not. We have to check.
Why do we have to check? What does the scalar multiplication identity say?
One
There has
belongs
to
the
be
field.
an element in the field. It has nothing to do with the subset of V, right?
Yes, sir. Then this also we do not need to check.
Exactly. We need not check this as well. How about closure with respect to scalar multiplication?
These
Also not.
Oh, not required. Why not?
Sir, we require to close this.
No, we require.
yes,
We
these will
require,
be
right?
required.
We just,
Of
in
course.
fact, we proved that this straight line that does not pass through the origin is not a subspace because it violates this, right? It is not closed with respect to scalar multiplication. So this, of course, is required. How about the first one? So abelian group that contains 5 axioms, right? It summarizes 5 axioms. Commutativity of addition, do we need to check for a subspace?
No.
No,
No. Associativity,
no,
No.
No, sir.
not required. What else?
Existence of identity.
Existence of identity, do we need to check?
Yes, sir.
Yes.
Yes.
So maybe I'll write it over here. What more? Closure?
yes, we have to check.
Yes, sir.
Or. Right?
And so the existence of inverse also.
Existence of inverse also. Good. Okay, so that, I mean, you can see that more than half of these axioms, more than half of the vector space axioms, we need not even worry about. Okay, so we'll sort of soon summarize what is it that is required for a subset to be a subspace. And I think I have one more example of a subspace. Again, trying to give you an example from your signals and systems. Let us consider the set of all finite energy continuous time signals. Can you identify what is W? If you have studied Fourier transform, you should be able to identify what is this subset W.
Power signals.
No.
Periodic signal.
No. I mean, does this capture periodicity?
Odd signal.
Once again?
Odd signal.
No. What is an odd signal? Odd signal is f of minus t is equal to minus f of minus t, right? Or yeah, whatever. I mean, what does this capture? You studied Fourier transform, right?
It is a signal like sine and all who
No.
have same
Same what?
same in upward to the x-axis and
But
downward.
then why does it have to be like sine? So the left hand side is what? This is nothing but your DC
Area.
value, right? DC value or the average value.
Function symmetric about x-axis.
Exactly. So that's nothing but your DC value of the signal, isn't it? You study DC value, I'm sure, even in your, I don't know, basic electronic circuits course, isn't it?
Yes.
So this left-hand side is nothing but the DC value. So W is a subset of all finite energy signals whose average value is 0. Okay, and that also, I hope you can see that it also forms a subspace. Do you want me to prove this, or can you do this yourselves? So for example, let's show closure with respect to addition. So if F and G are two signals, finite energy signals whose average value is 0, how about the average value of F plus G? What would this be equal to? By exactly this, by definition, is this plus this, and we know this is 0. This also is 0, so 0. Okay, so F plus G also belongs to W. Then scalar multiplication closure. What is the average value of A dot F? In by definition, this is A
Yeah.
to FTDT, which of course is 0. Okay, so therefore, E dot F also belongs to W. Okay? Is it clear?
Yes, sir.
Okay, then now let's look at this proposition. A non-empty subset W of a vector space. So again, remember, this is important here. A non-empty subset. Okay, a non-empty subset W of a vector space V is a subspace if and only if W is closed with respect to vector addition and W is closed with respect to scalar multiplication. These are the only two vector space axioms that you really need to check. Try to digest this. So this is an if and only if statement. I think proof this way is straightforward, right? The sense that if W is a subspace, then it has to be closed with respect to this, right? Let me call this 1, let me call this 2, then 1 and 2 are satisfied. That comes basically from the definition of vector space, right? Because if I say W is a subspace, it has to be a vector space. If it is a vector space, of course, it has to be closed with respect to vector addition and scalar multiplication. Right? That I hope is straightforward. How about this way? If 1 and 2 are true, then W is a subspace. How do we show that?
Showing all required group axioms or
No,
subspace.
great. Yes, but can you try and prove this? Right. So, right, that you'll have to show each and every vector space axiom is true or is satisfied. Okay, but should we sort of go through this proof?
Yes, sir.
Okay. So, name the first vector space axiom.
Abelian group.
Abelian group. So W with plus is an abelian group. This is what we'll try and show. You guys should help me out now. What do we need to show for this to be an abelian group?
It is closed under the addition.
So that already is given, right?
Hmm.
W plus is closed. Okay, so that is done. Then
Identity.
identity. So how do we show identity exists? So from 2, right? You know that 0 into, so okay, let me do it step by step. What do we know about W? W is a non-empty subset, right? So there must exist some element U in W, right? Because it is non-empty. Moreover, 0 into U, right? So 0 scalar multiplication U also should be in W.
Yes, sir.
What is 0 into 0 scalar multiplication U?
Theta.
Why? Have we proved that?
We know that every element of U will be multiplied by 0, so all become 0.
No. See, this is an abstract vector space, right? So we have not defined, we have not taken an example of V or W. We don't even know how this is defined. Okay. Oh, I'm running out of time. So this will be a tutorial 3 question. Show that for any vector U in my vector space U, 0 into U is equal to theta. Just highlight this. This will be one of the questions. You'll have to prove this. So for now, let's just assume this is true. Since this is true, right? So therefore, U into 0 is theta, and that also should belong to W. Okay, so additive identity exists. That's done. Then what's the next property?
Inverse.
Inverse. How about inverse? Let U belong to W. Why will the inverse of U also be in W? Again, I'm running out of time, so let me complete this. From 2, right? So by 2, I mean this. W is closed with respect to scalar multiplication, right? What is minus 1 multiplied by the scalar, oh, sorry, minus 1 scalar multiplication U? Surely this is in W, but what can we say about minus 1 scalar multiplication U?
Minus U.
Why? So again, running out of time, so let me include this in the tutorial sheet. Show that for all u in B, -1 scalar multiplication u has to be the additive inverse of u. Okay, so for now, let's assume this is the case. So therefore, minus u also is in W. What else do we need in order to show that it's an abelian group? Or are we done?
Done.
Done, right? Right. What else? So we have done that W plus is an abelian group. What else is required? Go back there. Closure with respect to scalar multiplication, that is already given to us, right? And the other three, I mean, I hope you can see that we don't really need to check here. Scalar multiplication, identity, distributivity, and compatibility of field and scalar multiplication, right? Is that fine?
Yes, sir.
So we have therefore proved this proposition that W is the subspace of P. So again, analogous to the case of subgroup, right, where we simplified, we didn't need to check all group axioms. Similarly, for a subspace, as far as you're given a non-empty subset, we only need to check these two things, that whether W is closed with respect to vector addition or not, and whether W is closed with respect to scalar multiplication or not. These are the only two things that one has to check. I will stop after giving this one example. In case you remember the first module of linear algebra, where we took any arbitrary matrix of size m cross n, and we looked at 4 specific subsets related to the matrix A. Right? The column space, the left null space, the null space, and the row space. Again, I hope you, I am not sure whether you remember or not, but we proved certain properties that all these 4 subsets satisfy, right? Do you remember any of those properties? We basically checked whether the zero vector belongs to these 4 sets or not, and we showed that it does. And the other thing is, if there are 2 elements in that set, any linear combination of those 2 elements also belongs to this set, same set. Yes or no?
Yes, sir.
Right. So in principle, I hope you agree that we have basically checked the conditions given in proposition 1. Because linear combination is what? It's nothing but vector addition and scalar multiplication. Okay, so in principle, we have already proved that given a matrix A, right, its column space, its left null space, its null space, and its row space, they are subspaces of Rm and Rn respectively. Once this is proved, right, we'll call these 4 subsets as the 4 fundamental subspaces associated with the matrix A. Okay, and we'll stop for today. We'll continue our discussion about subspaces on Friday. Okay, so thank you, and see you guys on Friday.